Hello everyone. So for today's lecture, we're going to be learning about a new type of function today. So last class we talked about exponential functions. Today we're going to talk about logarithmic functions. Alright? We're going to get into some basic properties of logarithms, and then we'll finish off by discussing the graphs of these logarithmic functions. So let's go ahead and get right on into it. Okay, so before we actually get into the new information today, I want to go ahead and recall something. What I want to recall is what we talked about last lecture, that being the graph of an exponential function of the form a to the x. So we talked last time that if you have an exponential function of the form a to the x, then you can expect the general shape of its graph to look something like this, with a y-intercept at 0, 1. Now, in addition to this, I actually want us to dig back further and recall something else as well. That being our horizontal line test. Right? If you don't remember, the horizontal line test was a visual test we could use to determine whether a function has an inverse or not. And the test was pretty straightforward. All it said is, given the graph of your function, if there is nowhere on that graph that you can cross it at more than one point using a horizontal line, then the graph is an inverse, right? So we can see that quite easily. There is nowhere I can cross this graph with a horizontal line at which it's going to cross at more than one point. Therefore, the horizontal line test tells us that a to the x has an inverse. Right? So this tells us a to the x has an inverse. Now, we can expect, and actually I'm going to go ahead and erase these lines right here just to clear up the image. Now, we already know how to generate the image of this inverse then. We don't even have to understand what the inverse function is, but we've talked about before in this class how visually we can construct the graph of the inverse function given the graph of a to the x, right? So hopefully you recall, and if not, I actually encourage you to go and pause the video right now. Flip back to your notes and see, or if you wrote it down anywhere, what is the way in which we can construct the graph of an inverse function given the graph of the original function. So actually go and take a moment now to pause and look back through your notes. Okay, so hopefully you look through, and if you found it, great. If not, no problem. We're going to talk about it right now anyways. So given the graph of a function, and if we know an inverse exists, then we know that the graph of the inverse function will simply be a reflection across the line y equals x. So here's my line y equals x. So I'm going to take this image and I'm going to reflect it across this line, and whatever that produces, that will be the graph of my inverse function. And what we see, if we do it properly, is the image we end up producing is going to look something like this. Go ahead and clean this up a quick bit. We end up making an image something like this. Alright? This line in blue. So, this blue line is going to be our inverse of a to the x. So, the blue line is the inverse of a to the x. And the reason why I want to bother reviewing all this and coming to this point where we've constructed this blue inverse line is because what we're going to be basically talking about today is logarithmic functions. And the big core idea of logarithmic functions, the reason why we bother talking about them is because of this right here. Logarithmic functions are the inverse of exponential functions. This is the big connection between them. This is why we even bother talking about them. It is because of this inverse connection. And what we'll see is that's directly addressed in the definition of a logarithmic function. So why don't we go ahead and talk about that now. But before that, go and take a moment to pause the video and get this all copied down. Alright, so let's go ahead and address the definition of a logarithmic function now. Kind of a tongue twister. Okay, so here it is. Here's our definition of a logarithmic function. So it goes like this. For x greater than 0, a greater than 0, and again a not equal to 1, alright, we get to say that y equals log base a of x, so that's how we read this. And this is our, moving forward, this is our notation for logarithms. It's this new kind of like tool, like a square roots. We just call it log, all right? So we read this as log base a of x. All right, so log base a of x. And I guess I also threw in another mathematical notation we like to write. So this is a pretty common one, and it's helpful to know. Just makes reading math easier. This if with two f's, this means if and only if. If and only if. Alright, so just to start again. So for x greater than 0, a greater than 0, and a not equal to 1, y equals log base a of x, if and only if x equals a to the power of y. So again, as I've already mentioned, the idea that these exponentials and these logarithms are inverses of each other. Alright? If you plug in x to the logarithm, you output y. If you plug in y to the exponential, you output x. They're doing the exact opposite. Again, the idea, these are inverses. Okay? So, this is how we define a logarithm to be. And then we get to say the function given by f of x equals log base a of x is called the logarithmic function with base a, right? So hopefully you remember this notation from last lecture when we were talking about the exponents, right? Going back to this example up here, we said that this exponential function a to the power of y, we would say that a is the base. Same idea here. The number we write, and I guess I should point out, this a, and when we're using it for the logarithm, this is a subscript, if you're unfamiliar with subscripts. So you have things like superscripts, which are kind of like exponents. They're written above a value. So I have a superscript is written up here. The a over here is a subscript, so we write it below the a. So, and I want to go ahead and mention that because writing things like this would be incorrect, right? If you're trying to write, say, log base 3, I write the 3 kind of below the logarithm. I don't write it right next to it. There's a big difference between how we read these two. This is log base 3. I would read this as log of 3. So just a minor thing to point out, if any of you are unfamiliar with a subscript, that's what's going on there. But regardless, again, this subscript a is again referring to just the idea of the base. So, again, yeah, like I said, just these logarithm functions, the big idea of them is just this inverse relationship they have with the exponentials, kind of the whole point behind them. So with the definition out of the way, and if you haven't done so already, please take a moment to pause the video and get this all copied down. Right, so like I said, it's just kind of a new operation we get to use, kind of like a square root, but a lot different from a square root. So let's actually just go ahead and use it and do a couple examples calculating some logarithms. So let's do that now. Okay, so let's go ahead and do a couple examples of trying to solve some logarithms by hand. And to start, let's consider this following expression. Log base 3 of 27 equals what? Alright, so again, let me just go ahead and write that in words just so we get familiar with how to read these logarithms. So we would read this expression as log base 3 of 27 equals what value? Okay? And at least in regards to solving logarithms by hand, I find them quite nice because to me, solving these logarithms just becomes a game. And the game, or at least the name of the game, is directly going back to that definition we just gave for these logarithmic functions. In that we said y equals log base a of x if and only if a to the power y equals x. Okay? So, in the spirit of that definition, let's just go and assign the values we see in that definition with the numbers we have here, right? So, from that definition, our base a is 3. Our x is 27. and our y, the value the logarithm equals, is unknown. We're trying to find that y. And so what I'm trying to get at here is to solve this logarithm, the game we play is simply this. The game is take these values and just plug them into that second half of that logarithm definition, that after the if and only if, the exponential form. So we'll take these, and when we plug them into that exponential form, we end up with the question instead, 3, right, a to the power of y. So 3 to what power will equal x? So will equal 27. Okay? So in other words, just to kind of bring things all back together, in order to solve this logarithmic expression by hand, we kind of just don't really solve the straight logarithm by hand. We instead consider the exponential form as dictated by the definition of a logarithmic function, and then we solve this question instead, and the answer to this question will be the answer to this logarithmic question. So in regards to solving logarithms by hand, this is kind of what I do every single time, is I just consider the exponent instead. So it just comes down to this then. What power of 3 makes it equal 27? So we simply have to walk through our powers of 3. 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3, 27. There we go. So in other words, our question mark equals 3 because 3 to the power of 3 equals 27. So bringing it back up here, we equal 3. So log base 3 of 27 equals 3. Okay, so there's that first example. Now let's go ahead and just do a couple more, right? Get some more practice with this. If you haven't done so, go ahead and copy all this down though, because I'm going to go and erase it and just start with a fresh board. Okay, so for our next example, our next couple examples, let's consider the following questions. Log, I don't like how I wrote that. Log base 25 of 5 will equal what value? And log base 2 of 1 over 8 will equal what value? Okay, so let's consider these two logarithmic questions. And like I said, and let's actually go, and like I said, I consider these, I just look at these all as a game, right? So when I look at this first example, the game I ask myself is, right, going back to that definition, log base a of x equals y, if and only if a to the power of y equals x. In other words, 25 to some unknown power will equal 5. What must that power be? That's the question I'm asking myself. This is the game I'm playing. So we think about that. I have 25. I have some power. It's going to 5. So 25 is 25 is bigger than 5, right? So I already know my exponent has to be a number less than 1. I'm going to be taking a root somehow. Then we look and we just say, oh, well, there's the connection right there. 25 is a perfect square. It's 5 times 5. So what's the power of 25 that's going to bring it back down to 5? Well, I must be taking a square root. If I'm taking a square root, that means I have a 1/2 power. All right? So that first one, the question mark has to be 1/2. So up here, log base 25 of 5 equals 1/2 because 25 to the 1/2 power equals 5. So let's go ahead and consider the next one now, all right? So yet again, we're playing a game. So what I'd like you all to do now is go ahead and pause the video. Try working that problem on your own. Construct your game, walk through it, see if you can come up with an answer, and we'll go ahead and discuss it after you unpause the video. So go ahead and pause now. Alright, so hopefully you gave the problem a shot. Alright, and let's go ahead and discuss it. Again, we're playing a game here. For us, the game is... what power of 2 will make it equal 1 over 8, right? Our base is a. We're trying to find some power that will make this equal 1 over 8. Okay, so we just need to walk through and construct this. Now then, hopefully you have an answer. the answer I have is that this question mark has to equal minus 3. Okay? Has to equal minus 3. Now, how do I get that? Let's go ahead and walk that through, because it's worth talking about. Right? Being able to solve problems like this really shows you have a strong grasp in exponents. So for solving these problems without much difficulty, great, good job. If you're struggling a bit, no worries. This is a great time to practice, get some review in. So let's go ahead and talk about that with this example right here. So I have that I want 2 to some power will equal 1/8. Now immediately, we should be notice something. We should notice that, well, I have an 8 here, and I'm talking about powers of 2. So hopefully it clicks in our head that, well, 2 cubed does equal 8, right? Because 2 times 2 times 2 equals 8. So that's the same as 2 to the power of 3. So there is that connection, right? If that was just an 8, then I would say the answer is 3, but it's a 1/8. So that may trip us up a bit. We may be a bit confused about how we get the fraction, but hopefully after we think for a minute, we remember, oh, I'm talking about exponents, and my end result is a fraction when I started with a whole number. That must mean I'm using negative exponents, because we've talked about this before. We've talked about in class how negative exponents, all they simply mean is calculate the power like normal if it was a positive number, and at the very end you turn into a fraction. So with that in mind, and remembering that 2 cubed equals 8, that must mean my answer has to be -3, because again, since my end result is a fraction, I must be using a negative exponent. So hopefully that helped. That's kind of how I would have walked through this problem. If you have your own way of walking through it, that's great, as long as you have some understanding of why the question mark has to be -3 for this example. So here's another 2 quick examples for trying to solve logarithms by hand. Let's do another 2, and then we'll go ahead and move on. So the next 2 we'll consider are these. So I'm going to go ahead and erase this work right now. If you haven't done so, go ahead and pause the video to get this copied down. Alright, so the next 2 we'll consider are log base 79 of 79 equals what value, and log base 700 of 1 equals what value. Alright, so let's consider these 2 questions. And remember, we're playing a game, so let's construct the game. For this first one, the game is what power of 79 makes it equal 79. Alright, so think to yourselves, I got a 79. I need to take it to some power. Still want it to be 79. So nothing's changing, right? So without much difficulty, we can see that, this one is simply just 1. Alright? So log base 79 of 79 equals 1. So this example right here may seem like a pretty boring example. Kind of not doing much, right? We just have a base of 79, we just plug in 79, we outputted 1. Right? The reason why, because over here, what power of 79 is going to make it equal 79? Well, 1, right? So this may seem a bit boring, may seem a bit dull, but this example is actually extremely important, because what we've just shown right here is a pretty nice property of logarithms. The fact that if you have a certain base and you plug that base into the logarithm, the answer will always be 1, right? If we're ever able to get to the point where I know, given some function, that I can plug something in and get these nice numbers like 1 or 0, that's always an A+ in our book, right? So we always want things like that because it just makes nice numbers to work with. So again, kind of a boring example, but a pretty important example. This is a pretty powerful property of logarithms that we'll actually talk more about later in the class. So for now though, let's move on to this next example. We now have that log base 700 of 1 equals what value? So again, let's go ahead and leave this one to you guys. Go ahead and pause the video, work through it, try to see if you can figure out what the answer is. Remember the game we play. And after you unpause, we'll go and discuss it together. So go ahead and pause your video now. Okay, so hopefully you gave it a shot and you worked through it. And let's go ahead and discuss. See if our answers match up. So again, I'm just going to play my game. So the game this time around is, what's power of 700 makes it equal 1? Now this may seem ridiculously hard, like, wow, first off I gotta deal with the 700, that's such a big number, then I gotta talk about the exponents of 700, that's even worse, oh man, this is frightening, I'm sweating, but then we say, oh wait a minute, I just want this to equal 1 is all. Well, that's not so bad anymore. And why is that not so bad? Because it actually doesn't even matter anymore what the number right here is, right? If I'm just trying to find an exponent that makes some number equal 1, well, there's a magic number that does that. We talked about it before. It's one of the more important properties of exponents, that being anything taken to the 0 power always has to be 1. So right here, our question mark undoubtedly must be 0. Because 700 to the 0 power will indeed equal 1. And then up here, that also means that our logarithm value must equal 0. And again, just like this example, what we've just shown right here, that log base 700 of 1 equals 0. Alright, this, as we'll see later in today's lecture, is also yet another very powerful and useful property of logarithms. But for now, here's some just quick examples of solving logarithms by hand. Let's go ahead and move on to our next example. Okay, so before we actually move on to our next example, I want to take a moment to briefly talk about two very special logarithms that are used quite often that we definitely need to take a moment to talk about. So, for logarithms, we're at the edge. So for logarithms, right, we'll have log base a of some x value, right? So we're going to have, this would be log base a. So that base is important. Now, there are two logarithms in particular that kind of forego this notation and have their own special notation. One isn't quite different, the other one's only slightly different. And so I just want to point those out briefly. So two special logarithms. So, the first one I want to point out is simply just log. Alright? It has no base. Right? So there's no base. That's the key right here. No base written. Okay? So a log without a base is equivalent to log base 10. Alright? So a lot of the times when reading the textbook or just reading anything that involves logarithms, if they ever use log and they just don't write any base, it's because they're writing log base 10. And this is like, the reason why this is so is it's similar to that, the square root thing, where square root is the same as writing a 2 right there. But of course, we use square roots so often, and it's kind of the baseline when we're talking about any roots, that we just don't bother writing the 2. Same idea applies here. Log base 10 is kind of the baseline logarithm. Like a lot of things are taken base 10, like decimals and so on and so forth. So since this is kind of the like starting point, I would say, for logarithms, we just don't even bother writing the 10. We just kind of leave it out since this is the one that's used so often. Everyone just recognizes the fact this is just log base 10. So, moving forward in my lectures and examples, if you've ever seen me write log, just remember the base of this logarithm is 10. Now, the second logarithm worth pointing out is going to be ln. ln of x. Now, this is read as natural log. Or it's not. You would read it as ln, but this stands for natural log. Alright? And you probably have seen this before. I wouldn't be surprised if you have. And this, like log, has a special base. So this is log base e. Right? Remember we talked about e last class. So ln is simply log base e. Again, this is just another logarithm, this log base e. It just shows up all the time in real-world applications. That for someone out there said, you know what, this is special enough to give its own notation, we're calling this ln. Don't ask me why we don't call it nl. If it stands for natural log, who knows? We call it ln. So just wanted to point these out. Log with no base is the same as log base 10. ln is the same as log base e. These are our two special types of logarithms, and these are the ones, out of all logarithms, these are the ones that are used the most often. I'd say it's like, in real-world application, it's like a hefty, like 85% you use only these two, and like the other 15% use some random logarithms with some random base, but most of the time it's between these two that we use. So with that out of the way, let's now move on to another example involving logarithms. Okay, so for our next example, let's go ahead and consider these three logarithm evaluations. The first one being log of 2.5, right? So we want to know what log of 2.5 is. Well, just like our previous example, let's play the game. So that means we are then considering what power of 10, and remember, as we just mentioned, this logarithm is written without a base. That means it is base 10. So what power of 10 will make it equal 2.5? Okay? And so we sit there and we think about that, and we say, well, that's hard. I don't really know how to solve that question by hand, right? 2.5 isn't really a natural power of 10. It's not going to be a whole number power. And it's probably not going to be a fractional power either. So what the heck do I do here? And if you remember, last lecture we had similar problems like this where we solved similar exponentials and we didn't really know how to do them, so we had to go to and use our calculator. So it's going to be the same idea here, right? Whenever you have logarithms like decimal values or any logarithm of equation where you're looking at the exponential form and you say that's really not easy to solve by hand, in that case, just like we talked about last time, we just need to be using our calculator. And quite often it's going to be the case when you're handling logarithms. Most of the time they're actually not that easy to solve by hands because a lot of times you're going to be using these decimal numbers, and so we're just going to be needing to use a calculator. So on your calculator, again, hopefully you can figure it out. If not, make sure you look up a YouTube video on how to use your calculator to solve logarithms, or just meet me on Zoom. I'm happy to show you through Zoom. But it should be relatively straightforward because most calculators have a log button and an ln button. So to solve a log of 25, you would simply press the log button, input 2.5, and you would press enter. And so the value we get is, I'm going to have to erase this, is that this is approximately equal to 0.39794, and then we're going to round right there. Alright, so not a nice number. Definitely wouldn't have been able to do this by hand. Going to use a calculator. Similarly for ln of root 2. Again, this would imply the exponential form of e, because remember ln is base e. So e to what power equals root 2? Now that we're definitely not going to be able to solve by hand, so we're going to have to use a calculator. So actually for this one, go and pause the video real quick and try inputting this into your calculator, just get some practice. And after you unpause, I'll see what I get on my calculator and we'll go ahead and compare. So go ahead and pause now. Okay, so hopefully you gave it a shot, and let's go ahead and compare the answers we got. So when I plugged ln of root 2 in my calculator, I get approximately 0.34657. Okay, and I'm going to be rounding here. So this is what I got. So again, wouldn't have been able to do it by hand, going to be using a calculator. Now for the last one, let's go ahead and try this one. Log of -2. So again, we play the game and we say what power of 10 will make this equal -2. Now, actually, this question right here is going to be a bit different from the questions we already talked about, or bit different from these two examples up here. Because let's go ahead and consider this problem. And we're looking at exponential, okay? We're looking basically at when does 10 to the x equal -2? For what x, okay? So if we go ahead and consider the graph of 10 to the x, right, we can make a rough sketch. It's going to have to look something like this, okay? Going to have to look something like this. This is the graph of 10 to the x. Now, going back to what we just talked about last class, there's something we know about this graph. Right? We know that it has a horizontal asymptote at the x-axis. Right? What is so important about horizontal asymptotes? Well, that tells us this graph is never going to cross that horizontal asymptote. In other words, the value of this graph will never have a negative y value. It will always be a positive y value. So is it ever possible for 10 to the x to equal negative 2? No. It's not possible. Right? Function will never be negative. So, since this function is never going to be negative, then, going back to over here, this log of negative 2, it has no answer. Right? So this is a no solution. And also, I guess, what we could have also remembered is going back to the definition of logarithms. At the very start, when we said log base a of x, right before that in the preamble of the definition, we gave the condition that x had to be greater than 0. So just an important thing to note, why I wanted to bring this example up is whenever you're doing logarithms, this inside, and actually I'm going to go ahead and erase the graph right here to make room for this note. So you haven't done so already. Go and pause to get this graph written down and kind of this portion over here. Alright, so yeah, again, why I brought this example up. So this is a no solution, and why I wanted to bring it up is just so we're all clear in the fact that when you're handling any logarithm, doesn't matter what log, what base, no matter what the logarithm, that inside has to be a positive number. So the value inside a log has to be a negative, a positive number. Alright, if you ever have a negative value inside a logarithm, or you're trying to evaluate a logarithm of a negative number, that's going to be a no solution. Going back to the domain, right? So, in other words, this, we'll talk about that later. For now, when you're evaluating logs, this number inside always needs to be a positive value. Okay? So, yeah, so this was a pretty helpful example. Just wanted to illustrate the facts that, again, some logs will have no solutions if that value inside is negative. And for most of the logs we calculate in the real world, we have to be using calculators just because it's telling us to do these decimal or irrational numbers that we just don't have the tools to solve by hand. Now, here's a very important note in regards to these two examples when solving logarithms by hand. Since we are only allowed a scientific calculator in our class, we have to take important notes that these calculators only have buttons for log and ln. So a scientific calculator, and actually I want more room to write this down. So I'm actually going to go ahead and erase this whole bottom portion. If you haven't done so already, pause the video, get this bottom portion written down. Okay, so here's some important notes in regards to solving these logarithms with our calculator. So notes, when solving logs on a scientific calculator, when solving logs on with a scientific calculator, they only have buttons for log and ln. So they only have buttons for log and ln. In other words, if you want to say, in other words, they can't solve something like, I'm running out a bit of room, sorry about this. But, so what I'm trying to get at here is scientific calculators, what we're going to be using for this class, they only have options for log and ln. So log base 10 and log base e. In other words, if you wanted to solve something like log base 3 of 2.1, you couldn't solve that with a scientific calculator because of the base. Because this base is not e or 10, you can't solve it with a scientific calculator. It doesn't have the capacity to solve it. However, it's not the end of the world. We'll actually spend our next Monday's lecture, we will address the problem of then, since our scientific calculator can't solve this problem directly, how would we solve this using a calculator? We'll discuss that next class. But for now, I do want to mention and make it known that our scientific calculators can only do log base 10 and log base e. Alright? If you have any other base and you need to use a calculator to solve it, you got to do some other things beforehand. But we'll talk about that next class. Alright, so with that out of the way, let's go ahead and move now into a discussion of some of the more fundamental or basic properties of logarithms. Okay, so let's go ahead and discuss now some more basic properties of logarithms. We're actually going to spend our next Monday's lecture, we're going to spend the whole lecture talking about some more advanced properties of logarithms, if you want to put it that way. But for now, here we're just going to talk about the more core or fundamental properties of logarithms, just to get the ball kind of rolling. So to start with, our first property we're going to talk about is the fact that log base a of 1 has to equal 0. Okay? So we actually already talked about this example, or this property before in a previous example, that being that log base 700 example. And why do we say this was the case? Well, because a to any, or no matter what power, so anything to the 0 power, no matter the base, anything to the 0 power has to equal 1, right? That 0 exponent property. So just like we talked about that 700 example, what power of 700 makes it equal 1? Well, it has to be 0. So again, this is just coming directly from that 0 exponent property. So log base a of 1 has to equal 0. Now the second property of logarithms we're going to discuss for today also comes from that example we did before, that being what is log base a of a, right? So this is that, I think it was log base 79 of 79. What do we say that equals? Well, it has to equal 1. And why is that? Because a to the power of 1 equals a. Alright? So again, we've kind of already mentioned these two properties before in our previous example, just trying now to write them in a more formal manner. So log base of anything, so no matter the base, log base of anything of 1 has to be 0, and log base anything of that base has to equal 1. So here are our first two logarithm properties. Our next logarithmic property, something we've already mentioned as well, and that this property is going to be that log base a of a to the x. This will equal some value. We actually know what this is going to equal. So log base a of a to the x. Now, as I already mentioned, we've talked about this, right? What did we say is the connection between an exponential function, because that is what a to the x is, and a logarithmic function, right? At the very start of class, we said these are inverses of each other. So let's look what's going on here. I am plugging one function, this exponential, into another function, the logarithm. And I've already made the statements that these two functions are inverses of each other. So by the definition of inverse functions, we already know what this has to equal, right? This is the composition of two functions that are inverses, therefore this has to equal x by the definition of inverse functions. Alright? And remember, we talked about this before, when you're composing inverse functions, the order of the composition doesn't matter. The end goal should still, or the end result should still be x. So this is the composition of a logarithm and exponential in one way. We can go and flip the script as well. Alright? So in addition to the composition, or not, in addition to the plugging in the exponential into the logarithm, we could plug the logarithm into the exponential. So what I mean by that is something like a to the power of log base a of x. So here we replace the x inside the logarithm with a to the x. Over here we replace the x inside the exponential with the logarithm. So we've just flipped the order of the composition. So we just flip the order of the composition. Okay? And so just like over there, following through with our definition of inverse functions, this also has to equal x. So this property we've just written right here is just bringing together, again, that core idea that logarithms and exponentials are inverses, and that's why we call this third property the inverse property. Okay, so still one more property I want to mention. However, I don't want to jam it onto the bottom of this board. So I'm going to go ahead and erase the board. So if you haven't done so already, go and pause the video now to get these three properties written down. Okay, so let's go ahead and list off our last basic property for logarithms. And as I already mentioned, we'll talk more about some more advanced properties in next week's lecture. So, our last property for the day is this. Log base A of, oopsies, my bad. Okay, so the last property says that if log base A of x equals log base A of y, alright, then, so if log base A of x equals log base A of y, then x must equal y. Okay? So this is basically saying when you're dealing with logarithms, you'll never have the case where two different inputs create the same outputs. You will never see log base 3 of 2 equal log base 3 of 4. This will never happen. Two different inputs will never create the same outputs. Right? So this isn't always the case, right? We can consider different examples like 2 squared equals minus 2 squared, right? They both equal 4. So here's an example of two different inputs having the same outputs, right? This will never happen with logarithms. Every input will have its own unique outputs. So kind of a subtle but very important property of logarithms. And this idea of an input having a unique output is kind of an actual more powerful statement in mathematics. And it's something we like to refer to as, I'm going to go ahead and erase the blue, so if I haven't written that quick example down, please do so. Alright, so this property, this fourth property, is what we refer to as the one-to-one property. Why one-to-one? It's the idea of one input will go to one output, alright? It's a unique pairing. So, that's his last property I wanted to mention. And actually thinking on it, there is a point I want to go back to. So actually, go ahead and pause the video, get this copy down. I'm going to erase the board, and there's one last note I want to mention. Okay, so the last note I want to mention is going back to that third property, the inverse property. So our third property was the inverse property that said that log base A of 8 to the x equals x. And the note I want to make is that it's very important to recognize the base of the exponential and the logarithm are the same. Okay? In other words, this inverse property only applies when you have the same base in the logarithm and the exponential. A quick example of what I'm trying to get at. Log base 2 of 2 to the x does equal x. But log base 2 of 3 to the x does not equal x because they have different bases. So indeed, this second example is the composition of an exponential and a logarithm, but these exponentials and this exponential and the logarithm don't have the same base, so they are not inverses of each other. To be inverses, you must have the same base. Okay, last note I wanted to mention, an actual important one. So make sure you get this copy down, and once you get that done, we're going to go ahead and move on into a discussion of the graphs of logarithms. Okay, so to go ahead and start our discussion about the graphs of these logarithmic functions, I want to go ahead and graph this example. Let's graph log base 4 of x. And the reason why I want to do this is because last time, in our last lecture, we took the time to graph 4 to the x, okay? And we now understand, through that definition of logarithms, that these two are inverses of each other. So if I understand the graph of 1, that being 4 to the x, I can easily understand the graph of the logarithmic function, right? Because since they are inverses, the graph of log base 4 of x should just be a reflection across the line y equals x of this exponential graph. So let's go ahead and just do just that. So we made that list of points last time, so let's go ahead and just recopy that down. So for 4 of the x, we had the table of points. We had -2, 1 over 16, -1, 1 over 4, 0, 1, 1, 4, 2, 16, and 3, 64. Okay? And so that let us create a sketch of the graph. So like 64 is all the way up there, like 16 will be down here, then 4, then 1. Okay? And so that let us, 1, 2, 3. So let's make a sketch like this. So that made us make using this table of points, we can create a sketch like this for our exponential function, 4 to the x. Now, going back to what I've already said, since we understand the logarithms, or since we understand that the log function and the exponential function are inverses, we then know that the graph of these images are going to be a reflection of each other across the line y equals x. So let's go ahead and put that in here. Y equals x, okay? So, when I want to create the graph of log base 4, we actually can already do this pretty quickly just using what we have written down right now. And where that's going to come from is this table of points right here. Remember, the relationship between inverses and the relationship between functions that are inverses of each other. One of the big ideas was for a function, if you have an input that creates an output, the inverse is going to go the other way. So one input creates an output in a function. The inverse function will take that output and we plug it into the inverse function. It'll output the input. Wow, that sounds really confusing. What I'm trying to get at is, remember we did write at one point that if a comma b is a point on a graph, then b comma a must be a point on the inverse graph, right? So the input and the output, they swap positions. So the same thing's going to happen here for these exponential and logarithm graphs. So if we have our table of points, then for log base 4, if we want to make a table of points for this function, all we need to do is take this table right here and just swap them. All the y's will become x's, and all the x's will become y's. So I have 1 over 16, minus 2, 1 over 4, minus 1, 1, 0, 4, 1, 16, 2, and 64, 3. So there you go. We have the table of points, just got to plot them. So plotting all these down, and this is definitely not to scale. I guess I should emphasize that right now, that this graph is undoubtedly not to scale, but it'll suffice for us. So we're going to get something that looks like this pretty much. Alright, we're going to get something that looks like this. So this is that log base 4 graph. And so last time, in our last lecture, when we were just considering this exponential graph, at this point we made some observations about it. We talked about how it's increasing, how it's continuous. We talked about how it has an x-intercept. Let me use a different color. How it has a y-intercept at 0, 1. We also mentioned how there is visual evidence of a horizontal asymptote at play. And we went on to talk about what it means to be a horizontal asymptote. So we're going to do the exact same thing today, just a bit differently, right? Because we have reflected the image, and hopefully it's not too much of a jump to kind of come to understanding that whatever properties this graph is going to have, the exponential graph, the logarithmic graph is going to carry over those properties and just have them in a slightly different form, right? So a great example, here we had a y-intercept. For the logarithmic graph, we're still going to have an intercept, but this time it's an x-intercept. So we have an x-intercept now. So before we had the y-intercept 0, 1. For the logarithmic graph, we're simply going to have the x-intercept 1, 0. Right? This graph is also continuous. This graph is also increasing. Another slight different change is before we had the horizontal asymptote. So when we reflect this image over and we get our blue logarithmic curve, it's not like the concept of the asymptote just vanishes and this graph no longer has an asymptote. It actually still does have an asymptote, just not a horizontal one. And I briefly mentioned it last time. It's our second type of asymptote we're going to be concerned with in this class. So this time we have a vertical asymptote. Okay, so just like last class, I wanted to introduce this idea. Now we'll go and move on. I'll give a formal definition to what it means to be a vertical asymptote. And after that, we'll go ahead and list some general characteristics about the graphs of logarithmic functions. So for now, let's just understand formally what is a vertical asymptote. Okay, so to yet again take a brief aside to talk about asymptotes, this time around we're going to talk about vertical asymptotes though. So a vertical asymptote, the formal definition for it is the line x equals a is a vertical asymptote of the graph f of x if f of x approaches infinity or f of x approaches a negative infinity as x approaches a. Okay? So hopefully you can see how this is very similar to that horizontal asymptote definition we presented last class, right? But the difference is this time being, instead of having a line y equals b, we now have a line x equals a. So in other words, instead of a horizontal line, we have a vertical line. Also, this time we're letting the function approach the infinities. Last time we let the x value approach the infinities. And remember, the arrow just means approaches in mathematical language. So this time around we're letting the function approach the infinities as the variable approaches a set value. Okay? So going on into the visual example then, we can kind of see what I'm trying to get at here with this definition, right? As x, so here's our x, I guess I forgot to label them, x and y. Right, so as the x value gets closer and closer to this a, so as we move towards as we move towards a from the right, we can see that as we get closer and closer and closer, the function starts going up and up and up, right? So the closer we get to this a, the more likely as we get closer to the a, the more this function is going to start shooting up. And so what ends up happening is you get infinitely close to a, and as you get infinitely closer to a, the more this function shoots up and up towards positive infinity. Same is true going in from the other direction, right? So here's just the other example you could see for a vertical asymptote. Our graph is coming in towards, from the right, I'm probably saying this wrong, whatever. But as we approach from this direction to the value of a, right, we get closer and closer in a, and the more and more that function shoots down towards negative infinity. So going back to that example we just had for log base 4, right? I guess I can sketch it, a quick sketch up here. So for that log base 4 function, we had it where we had something like this, right? So yet again, that y-axis will be our vertical asymptote, and as we get closer and closer to that y-axis, then more and more, the faster and faster that graph starts shooting down towards that negative infinity. So yet again, that is a visual sign that we have a vertical asymptote at play. Just something we have to be aware of when we're talking about these types of graphs. So that also means, and again, remember, that means we can never cross this line x equals a, right? This function never actually crosses it. So same thing over here. We can never cross the y-axis. Therefore, we can never use the negative portion of our x-axis, so we can never use those negative x values. And we'll actually see that when we go ahead and list the common characteristics of logarithmic graphs, which let's go ahead and do so now. But first, go ahead and pause the video, get this definition, get this definition written down, and let's go and talk and make some general statements about the graphs of logarithmic functions. Okay, so just to go ahead and list off some common characteristics about logarithmic graphs, we can note the following things, right? So if we take a basic log base A graph, right? So any log graph, any logarithmic function where it's just log base of some value of x, it will have these following characteristics. First and foremost, in regards to the domain, right, visually we can understand that, again, we've already mentioned it, how we're never going to be using these negative x values, and actually we're never going to be using the 0 value either, because as we'll mention briefly, since the vertical asymptote will be at this x equals 0 line, or in other words the y-axis, we never touch or whenever we cross the vertical asymptote. So therefore the domain of this function is 0 to infinity. Please note that we have a parenthesis on 0. We can actually never use the value 0. So, and also range-wise, so the range is a bit tricky because visually it does look like this line is flattening out. So it may imply that there's another horizontal asymptote that's going to stop this line. But actually, it just slowly, it's still going to be increasing forever. It just does so very slowly after a certain amount of time. So the range for this function is actually negative infinity to infinity, right? So the negative infinity is pretty clear. Our function's shooting down towards that negative infinity value. And what I encourage you to do is actually just graph a log function and just keep on watching it grow and grow and grow. The more you keep on expanding out your window, you will see that even though it may look like this is going to flatten out, it actually doesn't. It just slowly keeps on increasing. That's why our range is from negative infinity to infinity. Another observation we can make, we've already talked about it, is that we have an x-intercept. So instead of a y-intercept, we now have an x-intercept at 1, 0. The reason being, right, this relates back to that first property we made about logarithmic functions. That's exactly what this is coming from. Next, after that, the big one, I guess, is that the y-axis is the vertical asymptote, or in other words, the line x equals 0. So yeah, our y-axis before, for the exponentials, the x-axis was the horizontal asymptotes. So for logarithmics, the y-axis will be the vertical asymptotes. Again, as we mentioned in the domain, this means we will never use negative x values, and it also means we will never use the value of x equals 0 for the log functions, because we can never cross and we can never equal the vertical asymptote. The next observation we can make, I guess I should number these. And yeah, the last observation we make is just like for the exponentials, this graph is continuous, there are no breaks. This graph is also increasing, right? As we read from left to right, the values are getting larger in the y direction. So, continuous and increasing. Alright, so yeah, here's just some basic ones, basic observations we can make. The ones of important notes are definitely the domain, the x-intercept, and the vertical asymptotes. But regardless, besides that, that was pretty much all I wanted to talk about for the graphs of logarithms. So just end, actually, you know, that's a lot because there's another important point I want to get at, but we're going to do that in an example. So let's go ahead and try working on another graphing example now. Okay, so before we get into our last example and our last graphing example, start. Okay, so before we get into our next graphing example, I want to go ahead and make two notes about graphing logarithms. And what those are going to be is, well, if you remember in our last lecture, we went through several quick examples about graphing exponential functions, and they all built up to the final conclusion we can make in that all these rules and properties we understand about translating and reflecting graphs, so like for polynomial functions, those still applied for exponential functions, right? So you could still shift an exponential function up by 2. You could still shift an exponential function to the right 3 units. We could still reflect an exponential function across the y-axis. All that type of stuff. So all those rules and properties still apply. So not going to bother building that up again for logarithmic functions because it's just going to be the same process. But yes, I do want to make the points that still all the rules and properties for translations and reflections apply to logarithmic functions. Alright, so we can still shift log functions to the left and the right. We can still shift them up and down, and we can still reflect them across the axes. So these rules still apply. Wanted to make sure we were aware of that. And then the next point I wanted to make us aware of was, yet again, going back to last lecture, in regards to exponential functions, we made the observation, after a couple examples, we noted that vertical shifts change the horizontal asymptote for exponential functions. In other words, if I move my function down 2 units, my horizontal asymptote is now at y equals -2. If I moved my exponential function up 3 units, the horizontal asymptote was then at y equals 3. So vertical shifts change horizontal asymptotes for exponential functions. So, yet again, don't want to bother building up the argument again because it's going to be the same exact process, just slightly changed. But hopefully you can easily believe me when I say that the same thing applies for logarithmic functions, just change the corresponding values. In other words, horizontal shifts will change the vertical asymptotes on logarithmic functions, okay? That's the next thing I want to be aware of. So, horizontal shifts change the vertical asymptote for logarithmic functions, for log functions. Okay? So again, horizontal shifts change the vertical asymptote for log functions. Vertical shifts change the horizontal asymptote for exponential functions. Just remember that pairing. Okay? So just wanted to point that out because it's definitely, we need to make sure we're clear on that. And now with this out of the way, let's go ahead and move into this graphing example to finish up the class for today. Okay, so for our last example for the day, let's go ahead and consider this following function. F of x equals log base 4 of minus x minus 2 plus 3. All right, and let's go ahead and graph this function. So again, right, now since we understand our rules of reflections and translations apply, we can hopefully easily see that all this graphing this function means is taking the parent function of log base 4 and doing a couple translations and reflections to that. So let's go ahead and list those off. What are the translations and reflections? Well, first and foremost, if my parent function is log base 4, I am adding a constant on the outside of that parent function. That's indicative of a vertical shift. So I'm going to have a vertical shift 3 units up. Okay? I also am subtracting a constant directly to the variable. That is indicative of a horizontal shift. So I have a horizontal shift 2 units. And remember, the horizontal shifts are the counterintuitive ones. So if I'm subtracting 2, I'm moving to the right. 2 units right. Next, I am negating the variable, right? So if we have a negation, negation tells us we have a reflection. And if I'm negating the variable, that's a y-axis reflection. So here are my 3 transformations. So all we have to do now is go ahead and apply each one. Now remember, best practice when we're doing transformations is to always do the reflection first. So let's start there. You know what? Actually, let's go ahead and have you guys pause the video now and try working through this problem on your own just so you can get some practice. Because we actually understand all the tools needed to do this problem. So go ahead and give it yourself a shot. And after you unpause, I'll go ahead and walk through the problem with you. Please take note. Do the reflection first, and then understand that this horizontal shift will change our vertical asymptote. All right. So be aware of how the vertical asymptote changes with that horizontal shift. So go ahead and pause the video now and give it a shot, and then we'll go and walk through it together after you unpause. Okay, so hopefully you gave the problem a try. So let's go ahead and just walk on through it. Right? So to start with, let's go ahead and just give a quick sketch of the parent function. So the parent function will have a vertical asymptote at x equals 0, and then it'll have an x-intercept at 1, 0, and the graph will look something like that. All right? So then, best practice, let's go ahead and do the y-axis reflection first. So at the start, I had an intercept at 1, 0. I'm now going to have an intercept at -1, 0. So creating that sketch and beginning something like that. Okay? So that's my new sketch. That's after I've done my reflection. Well, next I'm going to want to do my shifts. So let's go and do the vertical shift up. So my point -1, 0 will now become the point -1, 3. So 1, 2, 3. Now I'm going to have that point. All right, so quickly sketching that. We're then going to have some image that looks like this. Okay? Now, lastly, we have to apply the horizontal shift, and this is going to be the one that's significant note for, it's going to be of significant note for us, because this is where we're finally going to have to change the vertical asymptote as well. All right? So, just so things are not cluttered, I'm going to go ahead and erase this blue portion, just to give myself some more room with the image. So lastly, we want to take this image and we want to shift it. Oh, I guess I didn't erase it because we're moving to the right. We want to shift it 2 units right. So the -1, 3 will now become shifting over 1 will now become 1, 3. And what's important for us to note is that if I was at x equals 0 before for my vertical asymptote, I'm shifting 2 units right. So now that vertical asymptote will lie at 1, 2. We now have a new vertical asymptote at x equals 2. All right, so then let me go ahead and get rid of this. Then making a quick sketch of our graph, we expect it to look something along the lines of this. Right. Again, just to drive that point home, we are now crossing the y-axis, so it is not possible for that vertical asymptote to still be at the line x equals 0. It has to have moved somewhere, and we understand that the horizontal shift is what indicates where that vertical asymptote moves to. So this was a horizontal shift 2 units right. That is why our vertical asymptote is now at x equals 2. Okay, so that'll be it for today's lecture. We now have been introduced these two types of functions out, exponentials and logarithms. Next lecture, we're going to actually spend some more time talking about the properties of these logarithms, and then eventually we'll get into how to actually solve equations or functions that involve these things. But for now, we're still getting introduced to them. So that's it for today. Hope everyone has a nice rest of the day, depending on when you watch this. Continue to stay safe, stay healthy, and I'll see you guys in the next video.